So yeah, I'm Michael. I have the faintly ridiculous job title of I am a planetary computing fellow at the University of Cambridge. Um, and that job title kind of reflects that I'm I work for the computer science department at the University of Cambridge, but I spend most of my time working with ecologists and working on climate-related projects. Um, Before that, uh, I've been a contractor, and before that, I was a product lead in a software security startup. And so I've moved around quite a lot, but at the moment, I'm working on this because it is a timely and pressing topic. And a few years ago, my now boss approached me when I was looking for new challenges and explained that they don't come much bigger than this, and here I am. Um, the computer science is in the way of climate science. The topic of this talk is going to look at how ecologists are using computing and the tools and the data around that. But it's also kind of born from frustration that I think computers tend to hinder as much as they help with a lot of these projects. And so the aim is to kind of highlight some of these friction points and hopefully, inspire people to work on some of these problems. And if we have time, I'll share a little bit about what I'm doing on that side. So the kind of motivation. Hopefully, most of you are aware of the kind of climate crisis that we find ourselves in. Normally, at this point, someone would give you an example involving carbon. I'm not going to do that. I'm instead, maybe if I can change slides, I will. I'm going to instead look at biodiversity, which is another important variable in sustaining the planet. What you see here is a heat map showing the species density across the planet. And so this is just for terrestrial vertebrates, but clearly you can see the tropical forests around the center of the planet. And indeed, those are home to 2/3 of the world's biodiversity. You hopefully can make out there the Amazon in South America on the left, the central belt of Africa in the middle, Madagascar next to it there, and Indonesia on the right. And in the middle of Indonesia, we have Borneo. And here's some data showing what's happened to those tropical forests in Borneo over the last 50 years. As you can see, we have been slowly whittling away at them, and there is very little of the kind of regional growth forest left in Borneo. And Borneo is not unique, unfortunately. This isn't some special case. If I look at the data for Sierra Leone or the kind of east coast of Madagascar or in the Amazon, you see this story playing out in many places. And given how important biodiversity is to sustaining the planet, that is suboptimal. So I work with a lot of people who are trying to tackle problems like this. I work at the Cambridge Conservation Initiative, which is an institute put together by Cambridge University, and they've put in a bunch of computer scientists like myself, zoologists, plant scientists, and then a bunch of NGOs in the conservation domain. So RSPB, which kind of is a familiar one in the UK, but also BirdLife International, the International Union for the Conservation of Nature, and other such NGOs. And the idea is you put us all in a building, shake it up, and hopefully, accelerate research in this area. My role in this, I liken to someone in the background of an Avengers movie. The ecologists are the superheroes here. They are literally trying to save the planet. That is their job. And I am there trying to enable them, empower them more. And that's because ecology has, like many domains, has become a data science. domain as much as anything else. There is a large wealth of open and freely accessible data sets about the environment, about animals and what have you. So here's just a small sample of things you can go and download and start playing with today. JEDI on the top left there is a NASA project where they've taken they've taken 8 lasers, stuck them to the International Space Station, and they fired them down at the planet, and the lasers will reflect off the different amounts off the various layers within forests. So you'll get some reflection off the upper canopy, then the lower canopy, then the understory, and then the ground. And so by they get those reflections back, they process that data, and from that they can tell the state of the tropical forests, whether they've been logged, whether they've been they're growing back, like how much biomass is in the area. And so it's just, to me, slightly mind-blowing that you can get away firing lasers off a space station and catch them again, but that's pretty cool. At the other end from NASA, you have citizen science. So the green icon in the bottom left is iNaturalist, which is an app you can get on your phone, and you log sightings of wildlife. And whilst that data set is incredibly biased, it is one of the largest point data sets of species we have. And so as long as you can account for that bias, it is an incredible data source, the like of which we've not had before. And so all of these data sets empower ecologists to start analyzing and coming up with new work. And the way they analyze and process this work is, by and large, with open source software. Everywhere you look around CCI, people are pretty much just using open source software. So we've got, in 3 of the corners, we've got Python, Julia, and R, which are open source languages that are the dominant 3 languages in data science. We've got GDAL, which is a geospatial library that is used almost universally for processing geospatial data. We've got libraries for trying to parallelize and express jobs like Apache Spark and Sedona. And then all of this ends up running on servers that are running Linux under the hood. And so open source software is everywhere, and it's enabling all of this great research. But at the same time, a lot of these tools were perhaps not designed for this originally, or if, like, Python has become a data science language, but I doubt that was its original intent. But even where they are designed for this, I feel there is a gap between the open source tooling being made available for knowledgeable computer scientists to use and for ecologists to use. And there's kind of a gap there that then causes a whole bunch of problems, which we'll go into. And it's not to, I want to be clear, I'm not saying that ecologists are incapable. They are domain experts in another domain. We shouldn't expect them to also be domain experts in computer science. There's this great paper by Mary Shaw about myths and misconceptions of software development, where she looks at common assumptions around software development and tries to stack that up against real-world data. And she has this great term of vernacular software developers. These are domain experts in something else. I've got a friend who's a civil engineer who spends a lot of time writing Python scripts to analyze data for buildings, for instance. He would be a vernacular software developer. And that's how I class the ecologists as well, right? They are domain experts in zoology, plant science, or what have you, but they shouldn't also have to be domain experts in computer science. And my argument is that the tools and artifacts that we, the open source community, have provided them really aren't up to scratch, given the importance of the challenge that the ecologists are having to deal with. Hopefully that makes some kind of sense. So to highlight this, I'm going to walk you through a project which was called Life. I'm not responsible for naming projects, and so I can't justify the backronym here. but this was a kind of free air project by getting on for a dozen people, and involved a lot of compute. And along the way, we saw a lot of these frustrations that I'm talking about, and I'm going to kind of run through them. But first, so what is life? This map here is one of the outputs of this project. It is a map that shows the increased probability of species extinction if you convert that cell of land to arable, i.e. a farm. And so this is a result of, I say, a lot of work, a lot of compute, to tell you, please don't put a farm in the Amazon, which may seem obvious, but seems we keep trying to do that. And so we do need maps like this. The different colors are showing different taxonomical groups like amphibians, mammals, what have you. But you can clearly see it is kind of suboptimal to put a farm where we think most of the biodiversity is. It also produced this map, which is a kind of inverse, which shows the corresponding decreased probability of extinction if you revert human changed land back to its natural state. And this is, I find this map quite interesting as a non-ecologist, because it's not all positive. In the UK, we've got a landscape that has been arable for quite a while now, and so a bunch of species have thrived in that wouldn't have thrived in the natural state. And so rewilding doesn't always have this all animals benefit that everyone assumes it is. And so there's awkward conversations to have there. And so hopefully this can make those more data-driven. I mean, the EU has said it wants to rewild 10% of land by 2030. And so hopefully maps like this can go to inform that discussion. So the kind of first view on this. Data lineage and code lineage. I mean, I feel a bit silly having to qualify this because you'd hope in all endeavors, particularly science and engineering endeavors, you would want to be able to show you're working and keep records and demonstrate that you are doing a good job. I feel that in climate science that has become particularly important because there is a lot of money tied up in certain aspects of this, and that encourages bad actors. And so last year, The Guardian had this expose on carbon credits. So there's a lot of companies that want to do carbon offsetting, and so they're happy to pay for projects that claim to be offsetting carbon. But it takes a while for projects to spin up. And so there is a gap there, right, where unscrupulous people can come in and take money if they just claim to have done something that they haven't. And so there was a lot of bogus science that was exposed in this investigation here. And so it is really important that if you are trying to make claims about climate work, that you are really able to show you're working, let people challenge it, scrutinize it, and reproduce your work. For the LIFE project, this here is the pipeline of the software that generated those two maps. I picked this project because it's a nice kind of reasonably comprehensible pipeline. At the bottom, you can see the two maps that I showed you earlier. And then kind of going top to bottom, we have kind of data ingest layer. We have, and then the kind of next fifth is data hygiene, transforming the data, making sure all the maps align and they're the same resolution, what have you, just kind of data reprojection. The middle strata is a whole bunch of number crunching to do a standard ecology technique called area of habitat, where you can work out where the animals are. And then the kind of next tier down is doing a bunch of work specific to this project. And then finally, you've got a kind of reduced stage where you take all that data and generate the maps. And this is a nice after the fact view by by me coming at it as a software engineer as I am. But that's not really what happens over the course of 3 years in these projects. You have essentially this is science, this is research. These people literally don't know what they're doing when they start because that's their job. And so you'll have this situation where research, Alice will download some data and try and derive some learning from it, and she'll get that done and she'll pass it to Bob. Bob will try and write a script to mix it with some other data set that they've got, and that doesn't work, so he passes that to Carol, and Carol gets that working, passes that, blah, blah, blah. And over the course of 3 years, you end up with some results. But at no point during those 3 years did you have the nice kind of software diagram that I showed you to start with. And actually, it's even messier than that, because even that simplified one was a slight lie, because I cut out one of the variables. There were, for the actual paper, this is the software pipeline that was run. And in that kind of that passing data around and people running different scripts and passing their scripts around, and some of them using Git and some of them are not, and kind of the kind of just normal human flow of a project, a lot of information gets lost, and thus making it hard to generate these maps, and then when challenged say, oh no, I know exactly what happened, and enable someone to reproduce them. And that's kind of particularly frustrating to me, because the computer knew what was going on. It just chose not to save it. Like, if I download a file on this Mac, the security part of Mac OS will tag like the originator source. These kind of techniques exist, but they're not on by default. So this is a small demonstration hack that I did. All of that pipeline is written in Python, and Python is amenable to no end of tomfoolery because it's a dynamic language. And so I just wrote a module that would, if you imported it, you don't have to do anything else with it, you just import it. It shims all of the file open and network requests. And then when it writes the file, stashes that along with some other information, like if it finds a Git repository, like what version of the code was being used, it just stashes that next to the output file. And if it finds one of those stashes on its inputs, then it propagates that. And so just doing something like that, I can have at the end, I can have an artifact with the final map, where if I query it, I can see not just what went into it, I can see all the way back up to the primary inputs. And that doesn't scale because it's abusing the dynamic nature of Python. But there's no reason you can't build that into, say, a container environment or an operating system to propagate this. But it's not done, and non-computer scientists aren't aware of how to kind of do this in a reasonable time such that they can get on with their other jobs. A lot of the information in there, it's probably hard to read, is all of the Python libraries. The reason I stashed those in is because one of the bugs we hit along the way, or not bugs, one of the discrepancies we hit along the way was this map here. GDAL, the popular geospatial library, in a point update, fixed a bug to do with how slope is calculated from elevation. So it was good, they fixed a bug. But it meant that if you had calculated your data on the previous version, you couldn't reproduce it on the latest version. And so it's not just what version of the code did I run? What version of the data did I download? It's also what version of every library that I had installed went into making this result. Like, you have to snapshot the whole stack. Okay, so that's kind of a bit about lineage and about reproducibility. I'm going to try and teach you all how to do a basic ecological method that was in the middle of that diagram now. And there's a reason for this. So area of habitat is, I spent a lot of time generating area of habitat maps. An area of habitat is an attempt to work out where a species lives. And so we start with this. This is the IUCN Red List. This is the where everyone goes to see what the most endangered species are. If you go around a wildlife farm in the UK, you probably see this data on next to an enclosure or a pen. So here we're looking at a page for the bush hydrax, this small rodent. And you can see in the middle, there's a range map, which is just, there's a polygon saying roughly where this species exists. It has information like habitat preferences. So it says savanna, rocky areas, cliffs, mountains. So this is the kind of habitat that this species likes. And it'll have other information like elevation preferences and what have you. And so we can take all of this information and combine it with other data sources that are openly available and do better than that crude range map to work out where the animal might be. So we take the range, we rasterize that as a binary bitmap, so 0 not in range, 1 in range. We can take a high resolution elevation map, and we can filter that so we know the upper and lower elevation preferences of the species, so we can turn that into another, in or out binary map. And when I say map, I mean bitmap, and when I say bitmap, I literally mean TIFFs, because that's the standard data format for all of these raster images, is the good old TIFF image format. And then habitat map, similarly, we sort of habitat preferences. We can take a derived raster map of what habitats are in what location and filter that. And then we just multiply those 3 images together and we have our area of habitat. Fairly simple, that even I as a computer scientist can understand it. And so that seems fine. So why did it, when I started this project, did it take them 3 weeks to calculate all of the data to generate those maps? It's just scale. So there are 40,000 species on the IUCN Red List that go into this. The resolution of the maps they're using are 100 meters per pixel at the equator. So they take about 150 gigabytes per layer. And so that's 3 layers. So that's almost half a terabyte of data just to do one species. And then that 40,000 gets multiplied by 4 different scenarios and 5 different extinction curves. So you're ending up generating an awful lot of compute time here. Now, as a computer person, you can come in and start saying, wait a minute, this is a worst case, right? Because we can see that the bush hydrax is only in a small subsection of the world, so we can crop those maps and get rid of a lot of our data requirements, right? So we can, and that's true of most species. You get lots of species that are only in a local area. And so let's say on average it's 10 gigabytes. So now I can process many more species. Like we have, the data sizes don't tend to fit on a desktop computer comfortably. But we have these AMD EPYC servers, which have like 256 cores and a terabyte of RAM. When I started, a terabyte of RAM seemed an insane amount of memory, and now it seems not much at all. But yeah, given that constraint, 10 gigabytes per species, okay, we can do 100 at a time, right? We've just we've sped up this pipeline significantly, which is fine until a moose comes along. Because a moose, elk, occupies most of the northern hemisphere. And so you're suddenly loading 75 gigabytes where you expected 10. And because you're running parallel jobs, there isn't much room in memory. And now you run out of memory. And now bad things start to happen. If you're lucky on Linux, that process will crash, or it won't crash. The Linux out of memory manager will be kicked in, and it will terminate the process. But Linux isn't actually that, it doesn't know who's got too much memory. That's a subjective evaluation, right? Too much is not a technical thing. So what it actually does is it terminates the next process that asks for memory. So that might be one of your other species, and you, in 40,000 by 4 by 5, you might not even notice it's gone, which is bad. If you're unlucky, it might be one of your colleagues' processes, in which case you're going to have an awkward conversation later in the common room. If you're really unlucky, and this happens on our servers about twice a year, it'll be a system service that asks for memory next. In which case, Linux will quite happily terminate that system service, leaving the machine inoperable and requiring a physical reboot. And even if you don't get to that stage, like Unixes don't traditionally cope well when they run low on resources. Ubuntu, the long-term support Ubuntu 22.04 for most of last year had a bug in it where if you got super low on memory, it would lose DNS, in which case it was like the system was gone because we would lose connection to our network attached storage where we keep all the data. And so it's not just enough that we try and explain to ecologists kind of parallelism and memory management now. They have to get it absolutely right, otherwise the consequences are high. So how do you do better? Like what else do they do? So this is Google Earth Engine, which for an ecologist is a dream. Google are just offering you their spare compute, of which one imagines they have quite a lot. It has installed in it a lot of those open datasets I already mentioned, ready for you to use. You just can load them in. You don't have to upload anything. They have their own Python and JavaScript APIs, so you can write code that just brings in these datasets, does some work, and you don't have to think about parallelism. You don't have to think about memory management, and it all just works. But it comes with a catch, which makes me very uncomfortable using it for anything particularly important. It's a proprietary system. I cannot reproduce this work outside of Google Earth Engine. The code is written to their APIs. So if, for instance, if it went away, because Google are not obliged to provide this, then that work is no longer accessible or reproducible. And Google have a history of canning products on a fairly frequent basis. So it makes me nervous from that point of view. It also makes me nervous because American corporations have a habit of denying access to cloud services from countries that the current US administration doesn't view favorably, which means that then a lot of this science is not accessible to a certain amount of the global population. And that might align with the kind of areas where we're trying to tell them how to run things such that it's better for the climate. That feels quite uncomfortable. And so I like what Google have done with Earth Engine, but I feel it is not something we should be relying on. We should be coming up with something equivalent on the open source side such that we can have all of these reproducibility, longevity properties that we want. Sources of truth. So a lot of these data sets are very large and cumbersome, and they don't fit on your laptop easily. And so they often get downloaded once by someone, put on a NAS drive somewhere, and then shared between people. But I find this slightly frustrating because at the end of 3 years and a bunch of different people moving through, which version of that, when was it downloaded, is all kind of lost. And so I try and encourage people to refer to primary data sources where possible. Like if you're writing a script to run your pipeline, get the data from the primary data source in the script. And so this is Zenodo, which is run by CERN, which is a cloud hosting for scientific data. So those maps, for instance, that I showed you earlier will be on Zenodo. And so I wrote just a little command line tool. If you gave the Zenodo ID and said, please download this, make it low effort for the ecologist to get the data programmatically from the primary data source. But when I was preparing the slides for this talk, it failed. And I was slightly taken back. I wrote this tool in Go, which is a kind of strongly typed language. And what had happened was just that someone at Zenodo they hadn't changed the API, they'd extended it. Again, for the best intentions, they're adding something new, something useful. But because this dictionary of formerly just strings now is of a mixed type, my Go program didn't know about the fact that it was strings or dictionaries and stopped working. And it's this propensity that, and I'm guilty of it myself, as software engineers, to fiddle with things and improve them without proper versioning. That goes against, again, the kind of long-term reproducibility of this thing. And again, will just lead people to sharing files that they downloaded or they know that someone else has a copy of. The versioning gets even worse for some datasets. This is the EU Joint Research Council dataset on land use change, which goes back to like 1990, and it has every year from 1990 has a map saying what the land was, whether it was forested, degraded, replanted, what have you. And it's a very useful dataset. And they update it every year as they get new data. But they also update it as they get new learning, which is good. Because satellites don't see forested, deforested, they see images in different spectra, and then some software is processing that into something more useful, and that improves over time. But the challenge is that they were publishing this dataset at the same URL every year, and so the historic data, say the data for 2004, at the same URL would change year on year, which means that like this map here is just, you can kind of see the orange bits of this map are where we downloaded the same data set on 2022 and 2023, and it's looking at the same historic year, and the orange pixels are the ones that have changed. It's quite a lot of data that has changed. And so again, we hit this because we had two people running the same software and they couldn't reproduce each other's results. And we discovered that this was happening. And again, it's all with the best intention, but because the people publishing it are not thinking with a computer science mindset, it doesn't get automatically versioned. It isn't kind of obvious that these things have been done. And that, I think, is just because the tooling assumes that that knowledge is on the user. Okay. Last one. I throw this one in just because it amused me personally. I quite like this map. This map is hopefully, evidently, a bit of software that's gone wrong, but I think it's quite nice, Mondrian. This sentiment was not shared by my ecologist friend when they brought this to me. The pipeline had been running for several months successfully at this point, and they came to me and said, like, what's happened? And so I dug in, and it's this. So this is a bit of Python. I've imported NumPy, which is the standard numerical library in Python. And in X, I've assigned a certain value. This isn't a unique value. There are other values that have this property, but it's a floating point scalar. If I put that scalar in an array, and then I do the same operation on the scalar and the vector, I get an ever so slightly different result. The error is within epsilon, which is the minimum allowed variance in a float. Like if CPU has a value whereby if floating point numbers are sufficiently similar, they're considered the same. And so the error is within epsilon for this CPU. But obviously, when you start adding it up 40,000 times, that 10 to the minus 16 ends up becoming significant. And why we hadn't caught it was before is we got a new computer. We got another AMD EPYC server, and it just happened to have a very slightly different set of flags on it. And for the 8-word wide vector operation, it had different rounding from what it did for 4-word wide on the previous generation. And so our solution in the end was we had to disable it. And that's fine if you're a computer nerd that is interested. And I must confess, I actually just filed a bug on NumPy, and they solved this one for me. So credit to the NumPy people for being so responsive. But they closed it as not a bug, right? Because it isn't a bug from their point of view. The CPU is doing exactly what it said it would do, but it is not expected by any normal human, I would advocate. So that's a litany of bugs that we've come across in the kind of, in the lifetime of a project. And all of those, I think, are solvable as a computer scientist, but they're not stuff that you should be having to deal with when you're an ecologist trying to do important research when we're in a pressing time that needs that research done, and more of it done. The kind of take home, I guess, is from a lot of this. And in a second, I'll quickly show you what I've been working on. But the kind of broader point here is, like, we, as software engineers, we build systems to achieve a goal. But I think often we forget what the kind of higher level goal of the users are. Or kind of what the broader surrounds. Open source software, particularly where it is often engineering and technology driven. That is a broad generalization, I appreciate. But I think there's enough of it that has caused frustration that I think we need more open source software kind of effort focused on how do we enable more regular users to take advantage of all of the great power and flexibility we have today without having to trip over all of these hurdles. The kind of little niche that I've been working on with my colleagues at the computer lab. This here is a shell script that one of the ecologists wrote to run one of our pipelines. A shell script is not a good. So it's better than not having a shell script. So, and it's quite a nicely written shell script. So I'll credit where it's due. But obviously, a shell script doesn't do anything like dependency analysis. And when you're working with large data sets and things that can take like 3 weeks to run, it's not obvious. And so as a computer scientist, you may think, well, I know, I want a CI system, which is what we took their project and turned it into a CI project. But the problem with a CI project is it doesn't scale. Like, I can do this once for one project, but I can't hand it to an ecologist to run after I've left. Like when I ran a software team, I paid someone full time to run a build system for me, right? It is not something that most ecologists have a tame CI person on their team. And slightly worse for us, because we're a computer science department, we picked one that is based on OCaml, which is a functional programming language. This is OCurrent, which is the CI system that powers the OPAM package management for OCaml. And even most computer scientists wouldn't want to maintain this because you write your descriptions in OCaml. And so clearly it was a nice to speed up that one project, but it doesn't scale. So instead, this is what I'm working on. This here is the documentation for the life pipeline, but it is also the executable description of the pipeline. So we made this observation when I was writing the documentation after we decided we could in no way give them the CI system, that actually if you write this documentation nicely, then and make sure all the paths link up, then you actually have a fairly good description of how to execute this project. And so all these diagrams I keep showing you of the pipeline are actually the abstract syntax tree in our tool called Shark, which reads in that markdown file of code blocks and extracts the execution graph. And we do a little bit of syntactic sugar to do wildcarding, and it knows when it sees a wildcard, it should just run that command for every output of the previous command. And so you get some built-in parallelism and things like that. And ecologists, I think, are familiar with that interface because they use things like Jupyter Notebooks, which again, mark down with embedded Python. And so this is kind of the avenue we're going down at the moment to try and make it easier to do the right thing without thinking, right? They don't need to document the things before publication anyway. So why not make that documentation an executable artifact that actually has benefit to them? Okay, I rattled on for quite a while now. So I'm very happy to take questions. There's a link to kind of our website and to the life paper if you want to know more. But otherwise, I'm very happy to chat even now, or there's my email. Please feel free to reach out and ask questions there as well. Done silence.
Thank you very much, Michael. Any questions?
I have a question.
Mm-hmm.
You mentioned sort of links to citizen science and things like that, and I just wondered, sometimes schools, sixth forms, they're looking for projects to get involved in. Is there any routes for young people into some of this?
That I don't know, but it's an interesting question, and I imagine someone at the CCI would know that. So I'm very happy to try and find someone who would. I mean, like iNaturalist, there is no barrier to entry. Like anyone can pick it up and use it. But obviously, for a school project, you probably want some more kind of stronger narrative about the kind of consequences of that action. And so yeah, I don't know, but I think that is an interesting question. So I'll see if I can find out for you.
Thank you, Michael.
Oh, thanks, Michael. That was very interesting. So would you say the upshot of all this is that Donald Knuth was correct all along, and literary programming is the way forward? Is that sort of the tagline, as it were?
I think it is one tool in the weapon. I absolutely, yes. Clearly, what we're doing follows in that vein very strongly. And I think the success of Jupyter Notebooks as a tool in data science also is a much bigger confirmation that literary programming has its strengths. But I think it has to be coupled with work at other layers in the stack. Like when I was I guess I find it frustrating partly because I spent my career hopping up and down the stack, and so I feel like a bit like a kid in a toy shop. Kind of, I want to work on everything. I can't. So like when you do the parallelism, obviously you're going to do kind of some level of statistical multiplexing to try and kind of get the best performance there. And as the moose demonstrates that sometimes you'll come a cropper there. But again, there's no reason why that should be. Like in VM scheduling, you can watch the size, the memory demands of the virtual machines, and you can freeze a virtual machine and swap it out to disk. Like Linux doesn't have any equivalent tools at the process level. But it's not, to me, novel that we might do that. It's just our operating systems still feel like they're based on 1970s design and assume that we're editing a few text files. So I think the literary programming is a key part, but I think it has to be coupled with a bunch of other parts in the stack that have to work together. There isn't one single solution, I guess.
I have an observation about that.
Mhm.
The thing that I heard or the thing that I thought of when you said about just now about the resource limitation is I think I've been looking at recently is basically sort of pools. So you'll just have a queue, if you will, rather than saying, oh, we're just going to run 100 things. Say, we're going to start with or try to do 100 until we sort of get to 90% RAM usage, and then we're going to wait until one of them finishes. So unless you have an extremely big job, this moose would simply hold things up and not, lead to the massacre of other processes.
Right, but what happens when, like, like I say, most of them are small, and then at some point, one of these errant kind of large species comes along, and so you will kind of start that job, and it will overwhelm the system, and so you need to be able to then either say it's idempotent, so I can just accept I'm just going to kill that one because I spot it's ramping up quicker than the others, and I'll restart it when it's quieter. And you have to hope it's idempotent because people use imperative languages, they tend not to think about the consequence of side effects in their code. And so I think that is good, but again, I think you need to make sure that the programming model supports that kind of restartability or something. Am I making sense there?
Absolutely, yes. I'm not going to say disagree, but I'm thinking that you start the thing up and it fails to start because it hasn't got enough RAM, so it just didn't start, and then the imperative, it just literally wouldn't have got started, and then you would keep retrying it and then put it in a sin bin because it failed 3 times. But then other jobs started.
No, I think I think I'm agreeing with you that that is a strategy, but I think it is again like I have late converter syndrome. Like I'm very enthusiastic about functional programming because although I learned it when I was young, I never really used it, and now I use it quite a lot, and it has properties that would make it much easier to do this kind of making sure things are throw away. Or you have to run them in containers and know that all the side effects are contained so that when it fails, I can restart it without any negative consequences. And so I do think that is a great strategy, and we should build that kind of into the systems. I just think there are a bunch of subtleties that you also need to cross off at the same time. But I think if you put it in place, maybe people will then learn to think more about writing idempotent things because they'll realize that, oh, my life would have been better if I'd also done this. So maybe I have this tendency to try and solve everything at once, which is probably not very helpful here.
Well, I have the same tendency, obviously, because I'm a computer programmer. And I always believe that the next time it'll work, even though I'm always wrong. But I was going to say, I think that one useful technique that you might consider, and this is a bit tongue-in-cheek, so warning, but you just like name and shame. So yeah, someone tried to start up a job and it killed, and you have an automatic monitoring of that, and then you like name and shame, and then whichever scientist it was did that probably wouldn't do it again.
Yeah, I must confess, it all does tend to people feel very bad when they are responsible for taking the machine down. And so that kind of happens a little bit already. But it is that then it's yes, but it's then knowing, also educating them so that they can make the link to what is it I should have done, which is also kind of obtuse at the moment. And it is a challenge because I said I didn't want them to become experts in computer scientists, and now I'm saying you have to educate them. So,
well, just give them enough knowledge to be dangerous.
Always. That's the point of any education, surely.
I did have, while I'm sort of interrupting, and apparently no one else is piping up, I did have one other question. So I want to make a kind of a nice visual demo of using GDAL. I was very intrigued when you had that there. Are there good sources of data? Because when I say demo, I just mean something that people can look at. So I'm making an open source library, or should we say not making, but like maintaining, because it's been around for ages. But I want to make a demo of it, like a nice looking demo of just GDAL, and say, oh, look, this is the sort of thing that you can get, and let people do that in a sort of a canned way. What would I Google for? Because I did try and find visual demos of GDAL-ish stuff, and I could not find any. So if you can give me search terms, or possibly I should just drop you an email, and then hopefully you'll be able to tell me, so we're not wasting everyone's time here.
Yeah, so like the standard example I give to people, just because it's the one I happen to know, is doing the area of habitat calculation. And the way I do that is if if I pick a species, I take a much much lower resolution elevation map and habitat map, and you just add a few layers together, you do some filtering, and I'm very happy to give you some CAN data to that effect if you drop me an email.
I will then. Thank you very much. That'll be wonderful.
Okay.
Michael, can I ask you a question? You mentioned rewilding.
Yeah.
In 2010, somebody lent me a book about chaos. And within that, there was they'd done a study on predator-prey cycles. They found basically the population oscillated between certain limits, but then they found if another predator came in, it completely changed that. And then when that predator left, the original population levels were not re-achieved. So I'm just wondering, how successful is rewilding, given that we've had the ultimate predator, i.e. human species, trampling all over everything?
I'm afraid I'm unqualified to answer that one. I think it is an interesting point, and I think one of the things that I've kind of try and emphasize with those maps is that they are part of a discussion. They are not the only part of. They don't tell you the answer alone. So to your point, like it may suggest that rewilding, central Scotland, or based on that data would be a good thing. But based on other information, might not work. So I think yeah, I can't answer that question, but I think these are complicated questions that you need to look at a lot of different variables on.
Okay, thanks.
I have one other interesting kind of slight anecdote, if I have a minute which I couldn't fit into the talk, but I think is an interesting one also from a computer science perspective to consider, which is, so you end up with these pipelines pulling in lots of data, and you want to publish them and share them and make them public. But one of the things I learned similar to that is that actually not all the data can be public, because a lot of so if you know where the last few of a rare bird is, that is exactly the kind of information that poachers want, right? And so if you're trying to make these maps showing where you need to do conservation interventions, that's the same inputs are going to help the people who are working against you. And so you can't make that data, the input data, public, but you want to be able to make the derived data public. And so there is a bunch of kind of security research kind of around decentralized privacy and things like that I think need to be brought to bear to this kind of topic. And so it's just another one from a computing point of view, if you're looking for interesting challenges in this domain. That I found fascinating. I'd never considered that we want to do everything open, but actually we can't because there are bad actors who would abuse that. And thank you to everyone for the kind words in the chat.
All right. Thank you very much, Michael. Very interesting. Any last question before we... Right. Because I appreciate Michael with a round of applause. You could do it physically, you could do it
Yeah.
online.
Well, thank you very much for having me. And I say, if anyone has any other questions, feel free to reach out to me.
Yes, that's
Thank
fine. I
you,
found it
Michael.
very, very interesting indeed.